Hello dear students, welcome to mathematics class. In this class, let us discuss the important property of the integrable function, that is, if f is bounded and integrable on closed interval ab, then mod f is also bounded and integrable on the closed interval ab, and also show that modulus of integration over a to b f of x dx is less than or equal to integration over a to b mod f of x into dx. So, this is the property of integrable function, which is Riemann integrable. Let us prove this one. Since f is bounded on the closed interval ab, it is given f is a bounded function. Then by using the definition of the bounded function, there exists k greater than 0 such that mod f of x is less than k for all x belongs to the closed interval ab. So, here this is the definition of a bounded function. If f is bounded, then there exists a real number k which is greater than 0 such that mod f of x is less than k for all the x belongs to the given interval ab. Now, this can be written as mod f of x is less than k for all x belongs to the closed interval ab. So, here mod f of x and mod f of x both are same. So, therefore, it implies that here also if f is bounded, then mod f of x less than k, then if mod f of x is less than k, then it implies mod f is also bounded on the closed interval ab. So, therefore, here we have proved that if f is bounded, then mod f is also bounded. Then further we need to move towards proving the another property, that if f is integrable, then mod f is also integrable. Now, since f belongs to R of closed interval ab, means if f is Riemann integrable function, there exists a partition P of closed interval ab such that UPF minus LPF less than epsilon. So, here this is the necessary and sufficient condition for the function f to be Riemann integrable. Here already f is Riemann integrable. So, therefore, we can write the condition UPF minus LPF is less than epsilon, and if this condition is true, then we can say that f is Riemann integrable. Let P is equal to A, which is equal to x naught, x1, x2 and so on up to xr minus 1, xr up to xn is equal to B. Be the partition of closed interval AB. So, therefore, this is the partition of AB. Now, let small mr and capital Mr be the infimum and supremum of f of x in IR, where IR is equal to what? The interval from xr minus 1 to xr, and Mr dash and capital Mr dash be the infimum and supremum of mod f of x in IR. So, therefore, it is our consideration, since f is bounded, there must exist infimum and supremum, and mod f is also bounded. So, therefore, we have considered the infimum and supremum of that function in the rth subinterval. Now let alpha comma beta belongs to xr minus 1 to xr, the rth subinterval. So let us consider the 2 points alpha and beta in the rth subinterval such that f of alpha is equal to capital MR means supremum, f of beta is equal to small mr, and mod f of alpha is capital MR dash and mod f of beta is equal to small mr dash. Means these are the 2 points in the rth subinterval such that f of alpha means supremum of the function f is at the point alpha and infimum of the function f is at the point beta. Similarly here for the function mod f. So mod f of alpha is equal to mr dash and mod f of beta is small mr dash. And now consider mod f of alpha minus mod f of beta. Consider this one, and this is less than or equal to mod f of alpha minus mod f of beta. So here we have one property of modulus function, that is mod of mod x minus mod y is less than or equal to mod x minus y. So by using this property here we have written the result, that is mod f of alpha minus mod f of beta is less than or equal to mod f of alpha minus f of beta. So therefore here we know that mod f of alpha, that is what mr dash minus small mr dash is less than or equal to capital MR minus small mr, because we have considered the points alpha and beta in the rth subinterval such that mod f of alpha is mr dash and mod f of beta is small mr dash. Similarly f of alpha and f of beta. So therefore it is the result. And now consider up of mod f minus lp of mod f. So here it is the upper Riemann sum for the function mod f in the partition P, and this is the lower Riemann sum of the same function mod f in the partition P. And by using the formula we can write that summation over r is equal to 1 to n. So while finding the upper sum we need to consider the supremum of the function. So supremum of the function is capital MR dash into delta r minus, this is the lower sum, that is summation over r is equal to 1 to n, infimum is small mr dash into delta r, and this is equal to. So here we can write the summation in common, that is summation over r is equal to 1 to n, and delta r is also common term in both the summations. So therefore we can write this as mr dash minus small mr dash into delta r. Then so consider this as the first equation. Now from the first equation we can substitute that mr dash minus mr dash is less than or equal to mr minus mr. So therefore this quantity is less than or equal to summation over r is equal to 1 to n mr minus mr into delta r, and this is less than or equal to summation over r is equal to 1 to n. Now multiply and separate the summation, that is capital MR into delta r minus summation over r is equal to 1 to n small mr into delta r, which is less than or equal to. So here this summation over r is equal to 1 to n capital MR into delta r, this capital MR is the supremum for the function f. So therefore this summation can be written as upper Riemann sum for the function f minus here small mr. So small mr is the infimum for the function f, and this summation is the lower Riemann sum for the function f. So therefore here UPF minus LPF, we already know that f is the Riemann integrable function. then UPF minus LPF is less than epsilon, right. So therefore, here we can write that UP mod F minus LP mod F is less than UPF minus LPF and is less than epsilon. So therefore, by using the transitive relation we can say that UP mod F minus LP mod F is less than epsilon. So therefore, by using the necessary and sufficient condition we can say that mod F is Riemann integrable or mod F belongs to R of closed interval AB. So therefore, now one part is completed, means here we have proved that F is Riemann integrable and bounded, then mod F is also Riemann integrable, right. So therefore, here we have completed half of the given property, and the next we need to prove that mod of here modulus of integration over a to b f of x dx is less than or equal to integration over a to b mod f of x dx. This one we need to prove. Now we know that minus of mod f of x less than or equal to f of x less than or equal to mod f of x. So it is the property of the modulus function, because here if mod x is less than or equal to k, it implies that minus k less than or equal to x less than or equal to k. So therefore, by using this one we can say that minus of mod f of x is less than or equal to f of x is less than or equal to mod f of x. Minus of mod f of x means it is the negative value of the modulus function and this is the positive value. So therefore, any function is lies between negative and positive values since it is the bounded function. So therefore, this is the consideration. Now this can be written as minus of integration over a to b mod f of x dx less than or equal to integration over a to b f of x dx less than or equal to integration over a to b mod f of x dx. So therefore, again this can be written as minus of integration over a to b, this mod f of x is nothing but mod f of x dx less than or equal to integration over a to b f of x dx less than or equal to integration over a to b mod f of x dx. Now by using the same condition, if mod x less than k, then minus k less than or equal to x less than k. Here suppose this is our x, right, and here is less than, here minus k and this is plus k, right. Now just compare this expression with the property of the modulus function. Now it is minus k and this is plus k and this total quantity is x. So therefore, here we can write this as mod of integration over a to b f of x dx is less than or equal to integration over a to b mod f of x dx. It is just by using the property of modulus function. If mod x less than k, then this is the condition, and if this condition is true, then we can say that mod x is less than k or less than or equal to k. So therefore, here k is equal to what? This integration over a to b mod f of x dx, and x equal to what? Integration over a to b f of x dx. So therefore, now apply the modulus for x, that is mod of integration over a to b f of x dx is less than or equal to integration over a to b mod f of x dx. So therefore, this is the theorem or this is the proof required. Hence, the theorem proved for the given condition. If f is bounded and integrable, then mod f is also bounded and integrable, and also this property holds good if mod f is Riemann integrable function. The next property or the theorem is, if f comma g belongs to R of closed interval AB, means if f and g are the two Riemann integrable functions and k1 k2 belongs to R, means these are any two real numbers, then k1 into f plus k2 into g belongs to R of closed interval AB, means here k1f plus k2g is also Riemann integrable function, and also integration over a to b k1f plus k2g dx equal to k1 into integration over a to b f of x dx plus k2 into integration over a to b g of x dx. So, this is the proof required. Now, let us prove this one. Let f comma g belongs to R of closed interval AB and k1 comma k2 belongs to R. So, let us consider the two integrable functions. They are given f and g, and these two are the real numbers. Since f belongs to R of closed interval AB, then it implies that k1 into f belongs to R of closed interval AB, since because we have proved one theorem. If f is Riemann integrable function, then k into f is also a Riemann integrable function. So, therefore, by using this property, here we have written that f belongs to R of AB, then k1 into f belongs to R of closed interval AB. And similarly, since g belongs to R of closed interval AB, it implies k2g also the Riemann integrable function by using the same condition. So, therefore, now we got that k1 into f is a Riemann integrable function and k2 into g is also Riemann integrable function. Here k1f and k2g, these two are the Riemann integrable functions. Now, we know that if f comma g belongs to R of closed interval AB, then f plus g belongs to R of closed interval AB, because by using the algebra of Riemann integrable functions, the sum and difference, they are Riemann integrable functions. So, therefore, if f and g are Riemann integrable functions, then sum of them is also a Riemann integrable function. So, therefore, we can write that k1f plus k2g belongs to R of closed interval AB, right? Because by using the condition f and g belongs to R of closed interval AB, it implies f plus g belongs to R of closed interval AB. So, now consider integration over a to b k1f plus k2g of x dx. Here this can be written as integration over a to b k1 into f of x dx plus integration over a to b k2 into g of x dx, because if f plus g is a Riemann integrable function, then integration over a to b f plus g of x dx can be written as integration over a to b f of x dx plus integration over a to b g of x dx. So, here if sum of two functions is Riemann integrable function, then integral of that means integration over a to b f plus g of x dx can be written as integration over a to b f of x dx plus integration over a to b g of x dx. And again here we have one more result, that integration over a to b k into f of x dx is equal to k into integration over a to b f of x dx. This is also already we have proved, and this also already proved. So, therefore, by using these two conditions, this total integral can be splitted like this, and again this integral can be written as k1 into integration over a to b f of x dx plus integration over a to b here k2 into integration over a to b g of x dx. So, therefore, this is the proof required. Here you have proved that k1f plus k2g belongs to R of closed interval a b, and integration over a to b k1f plus k2g dx is equal to k1 into integration over a to b f of x dx plus k2 into integration over a to b g of x dx, and this property is called as bilinearity property. This is the bilinearity property of Riemann integral.